Power source. Storage capacitor. To other exciter. Rectifier. Input lead auto transformer. Breaker. Noise filter. Contactor. Multi-lob cam single lobe cam motor. Trigger capacitor. Spark igniter triggering transformer. Bleeder resistor. Figure 4-66. Capacitor type ignition system schematic. All high voltage in the triggering circuits is completely isolated from the primary circuits. The complete exciter is hermetically sealed, protecting all components from adverse operating conditions, eliminating the possibility of flashover at altitude due to pressure change. This also ensures shielding against leakage of high-frequency voltage interfering with the radio reception of the aircraft. Capacitor discharge exciter unit. This capacity type system provides ignition for turbine engines. Like other turbine ignition systems, it is required only for starting the engine. Once combustion has begun, the flame is continuous. Figure 4-67. The energy is stored in capacitors. Each discharge circuit incorporates two storage capacitors. Both are located in the exciter unit. The voltage across these capacitors is stepped up by transformer units. At the instant of igniter plug firing, the resistance of the gap is lowered sufficiently to permit the larger capacitor to discharge across the gap. The discharge of the second capacitor is of low voltage, but of very high energy. The result is a spark of great heat intensity, capable of not only igniting abnormal fuel mixtures, but also burning away any foreign deposits on the plug electrodes. The exciter is a dual unit that produces sparks at each of the two igniter plugs. A continuous series of sparks is produced until the engine starts. The power is then cut off, and the plugs do not fire while the engine is operating other than on continuous ignition for certain flight conditions. This is why the exciters are air-cooled to prevent overheating during long use of continuous ignition. 4-41. Ident. 115 vac input. Warning. Cooling air. Exciter to igniter plug cable connector. Fan cooling air from cables. NIGN, Airbus 1, Boeing, DAC, top igniter plug. Anti-shock mount. Fan cooling air from cables. Bracket. Exciter to igniter plug cable connector. NIGN, Airbus 1, Boeing, DAC, top igniter plug. Cooling air. 115 vac input. Cooling air. Figure 4-67. Fan air-cooled exciter. Igniter plugs. The igniter plug of a turbine engine ignition system differs considerably from the spark plug of a reciprocating engine ignition system. Figure 4-68. Its electrode must be capable of withstanding a current of much higher energy than the electrode of a conventional spark plug. This high-energy current can quickly cause electrode erosion, but the short periods of operation minimize this aspect of igniter maintenance. The electrode gap of the typical igniter plug is designed much larger than that of a spark plug since the operating pressures are much lower, and the spark can arc more easily than any spark plug. Finally, electrode fouling, common to the spark plug, is minimized by the heat of the high-intensity spark. Figure 4-69 is a cutaway illustration of a typical annular gap igniter plug, sometimes referred to as a long-reach igniter, because it projects slightly into the combustion chamber liner to produce a more effective spark. Another type of igniter plug, the constrained gap plug, is used in some types of turbine engines. Figure 4-70, it operates at a much cooler temperature, because it does not project into the combustion chamber liner. This is possible because the spark does not remain close to the plug, but arcs beyond the face of the combustion chamber liner. Turbine ignition system inspection and maintenance. Maintenance of the typical turbine engine ignition system consists primarily of inspection, test, troubleshooting, removal, and installation. Inspection. Inspection of the ignition system normally includes the following. Ignition lead terminal inspection. Ceramic terminal should be free of arching, carbon tracking and cracks. The grommet seal should be free of flashover and carbon tracking. Figure 4-71. The wire insulation should remain flexible with no evidence of arching through the insulation. Inspect the complete system for security of component mounting, shorts or high voltage arching, and loose connections. 4-42. Gasket. Lower shell. High voltage air surface gap. Center electrode. Upper shell. High voltage surface gap. Cement. Sealing wire. Gasket. High voltage recessed surface gap. Terminal screw. Low voltage shunted surface gap. Insulator. Coupling nut. Figure 4-68. Igniter plugs. Check system operation. The igniter can be checked by listening for a snapping noise as the engine begins to turn, driven by the starter. The igniter can also be checked by removing it and activating the start cycle, noting the spark across the igniter. Caution. The high energy level and voltage associated with turbine ignition systems can cause injury or death to personnel coming into contact with the activated system. Repair. Tighten and secure as required and replace faulty components and wiring. Secure, tighten, and safety as required. Removal, maintenance, and installation of ignition system components. The following instructions are typical procedures suggested by many gas turbine manufacturers. These instructions are applicable to the engine ignition components. Always consult the applicable manufacturer's instructions before performing any ignition system maintenance. Figure 4-69. Typical annular gap igniter plug. Ignition system leads. 1. Remove clamps securing ignition leads to engine. 2. Remove safety wire and disconnect electrical connectors from exciter units. 3. Remove safety wire and disconnect lead from igniter plug. 4. Discharge any electrical charge stored in the system by grounding, and remove ignition leads from engine. 5. Clean leads with approved dry cleaning solvent. 6. Inspect connectors for damaged threads, corrosion, cracked insulators, and bent or broken connector pins. 7. Inspect leads for worn or burned areas, deep cuts, fraying, and general deterioration. 8. Perform continuity check of ignition leads. 9. Reinstall leads, reversing the removal procedure. 4-43. Figure 4-70. Constrained gap igniter plug. Evidence of arching. Evidence of flashover. Figure 4-71. Flashover inspection. Igniter plugs. 1. Disconnect ignition leads from igniter plugs. A good procedure to perform before disconnecting the ignition lead is to disconnect the low-voltage primary lead from the ignition exciter unit, and wait at least 1 minute to permit the stored energy to dissipate before disconnecting the high-voltage cable from the igniter. 2. Remove igniter plugs from mounts. 3. Inspect igniter plug gap surface material. Before inspection, remove residue from the shell exterior using a dry cloth. Do not remove any deposits or residue from the firing end of the low-voltage igniters. High-voltage igniters can have the firing end cleaned to aid in inspection. Figure 4-72. Gap description. Typical firing end configuration. Clean firing end. High-voltage air surface gap yes. P. High-voltage surface gap. Yes. High-voltage recessed surface gap. D. Yes. Low-voltage shunted surface gap. No. Figure 4-72. Firing end cleaning. 4. Inspect for threading of igniter plug shank. 5. Replace an igniter plug whose surface is granular, chipped, or otherwise damaged. 6. Replace dirty or carbonized igniter plugs. 7. Install igniter plugs in mounting pads. 8. Check for proper clearance between chamber liner and igniter plug. 4-44. 9. Tighten igniter plugs to manufacturer's specified torque. 10. Safety wire igniter plugs. Powerplant electrical systems. The satisfactory performance of any modern aircraft depends to a great degree on the continuing reliability of electrical systems and subsystems. Improperly or carelessly installed or maintained wiring can be a source of both immediate and potential danger. The continued proper performance of electrical systems depends upon the knowledge and technique of the mechanic who installs, inspects, and maintains the electrical wire and cable of the electrical systems. The procedures and practices outlined in this section are general recommendations and are not intended to replace the manufacturer's instructions in approved practices. For the purpose of this discussion, a wire is described as a single solid conductor, or a stranded conductor, covered with an insulating material. Figure 4-73, the term cable, as used in aircraft electrical installations, includes the following: wire single solid conductor conductors, solid conductor standard conductor. B. Figure 4-73. 2 types of aircraft wire. 1. Multi-conductor cable. 2 or more separately insulated conductors in the same jacket. 2. Twisted pair. 2 or more separately insulated conductors twisted together. 3. Shielded cable. 1 or more insulated conductors, covered with a metallic braided shield. 4. Radio frequency cable. A single, insulated center conductor with a metallic braided outer conductor. The concentricity of the center conductor and the outer conductor is carefully controlled during manufacture, to ensure that they are coaxial. Wire size. Wire is manufactured in sizes according to a standard known as the American wire gauge. The wire diameters become smaller as the gauge numbers become larger. The largest wire size shown in figure 4-74 is number 0000, and the smallest is number 40. Larger and smaller sizes are manufactured but are not commonly used. Wire size may be determined by using a wire gauge. Figure 4-75. This type of gauge measures wires ranging in size from number 00 to number 36. The wire to be measured is inserted in the smallest slot that just accommodates the bare wire. The gauge number corresponding to that slot indicates the wire size. The slot has parallel sides, and should not be confused with a semicircular opening at the end of the slot. The opening simply permits the free movement of the wire all the way through the slot. Gauge numbers are useful in comparing the diameter of wires, but not all types of wire or cable can be accurately measured with a gauge. Large wires are usually stranded to increase their flexibility. In such cases, the total area can be determined by multiplying the area of one strand, usually computed in circular mills, commonly used as a reference to wire size, when diameter or gauge number is known by the number of strands in the wire or cable. Factors affecting the selection of wire size. Several factors must be considered in selecting the size of wire for transmitting and distributing electric power. One factor is the allowable power loss, PR loss, in a line. This loss represents electrical energy converted into heat. The use of large conductors reduces the resistance, and therefore the PR loss. However, large conductors are more expensive initially than small ones. They are heavier and require more substantial supports. A second factor is the permissible voltage drop, IR drop, in a line. If the source maintains a constant voltage at the input to the line, any variation in the load on the line causes a variation in line current and a consequent variation in the IR drop in the line. A wide variation in the IR drop in the line causes poor voltage regulation at the load. The obvious remedy is to reduce either current or resistance. A reduction in load current lowers the amount of power being transmitted, whereas a reduction in line resistance increases the size and weight of conductors required. A compromise is generally reached whereby the voltage variation at the load is within tolerable limits and the weight of line conductors is not excessive. 4-45. Cross-section ohms per 1,000 foot. Gauge number diameter. Mils. Circular. Mils. Square inches 25 degrees Celsius. 77 degrees Fahrenheit. 65 degrees Celsius. 149 degrees Fahrenheit. 0000. 000. 00. 0. 1. 2. 3. 4. 5. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 460.0, 410.0, 365.0, 325.0, 289.0, 258.0, 229.0, 204.0, 182.0, 162.0, 144.0, 128.0, 114.0, 102.0, 91.0, 81.0, 72.0, 64.0, 57.0, 51.0, 45.0, 40.0, 36.0, 32.0, 28.5, 25.3, 22.6, 20.1, 17.9, 15.9, 14.2, 12.6, 11.3, 10.0, 8.9, 8.0, 7.1, 6.3, 5.6, 5.0, 4.5, 4.0, 3.5, 3.1, 212,000.0, 168,000.0, 133,000.0, 106,000.0, 83,700.0, 66,400.0, 52,600.0, 41,700.0, 33,100.0, 26,300.0, 20,800.0, 16,500.0, 13,100.0, 10,400.0, 8,230.0, 6,530.0, 5,180.0, 4,110.0, 3,260.0, 2,580.0, 2,050.0, 1,620.0, 1,290.0, 1,020.0, 810.0, 642.0, 509.0, 404.0, 320.0, 254.0, 202.0, 160.0, 127.0, 101.0, 79.7, 63.2, 50.1, 39.8, 31.5, 25.0, 19.8, 15.7, 12.5, 9.9, 0.166, 0.132, 0.105, 0.0829, 0.0657, 0.0521, 0.0413, 0.0328, 0.0260, 0.0206, 0.0164, 0.0130, 0.0103, 0.00815, 0.00647, 0.00513, 0.00407, 0.00323, 0.00256, 0.00203, 0.00161, 0.00128, 0.00101, 0.0000802, 0.000636, 0.000505, 0.000400, 0.000317, 0.000252, 0.000200, 0.000158, 0.000126, 0.00000995, 0.00000789, 0.00000626, 0.00000496, 0.00000394, 0.00000312, 0.00000248, 0.00000196, 0.00000156, 0.00000123, 0.00000098, 0.00000078, 0.0500, 0.0630, 0.0795, 0.100, 0.126, 0.159, 0.201, 0.253, 0.319, 0.403, 0.508, 0.641, 0.808, 1.02, 1.28, 1.62, 2.04, 2.58, 3.25, 4.09, 5.16, 6.51, 8.21, 10.40, 13.10, 16.50, 20.80, 26.20, 33.00, 41.60, 52.50, 66.20, 83.40, 105.00, 133.00, 167.00, 211.00, 266.00, 335.00, 423.00, 533.00, 673.00, 848.00, 1.070.00, 0.0577, 0.0727, 0.0917, 0.166, 0.146, 0.184, 0.232, 0.292, 0.369, 0.465, 0.586, 0.739, 0.932, 1.18, 1.48, 1.87, 2.36, 2.97, 3.75, 4.73, 5.96, 7.51, 9.48, 11.90, 15.10, 19.00, 24.00, 30.20, 38.10, 48.00, 60.60, 76.40, 96.30, 121.00, 153.00, 193.00, 243.00, 307.00, 387.00, 488.00, 616.00, 776.00, 979.00, 1230.00. Figure 4-74. American wire gauge for standard annealed solid copper wire. 4-46. 36. 35. 7. 6. 5. 34. 9. 8. 10. 4. 11. 3. 33. 12. 13. 2. 14. 32. 15. 1. 16. 17. 18. 0. 31. 19. 20. 21. 22. 30. 23. 29. 24. 25. 26. 27. 28. Wire. Figure 4-75. Wire gauge. A third factor is the current carrying ability of the conductor. When current is drawn through the conductor, heat is generated. The temperature of the wire rises until the heat radiated, or otherwise dissipated, is equal to the heat generated by the passage of current through the line. If the conductor is insulated, the heat generated in the conductor is not so readily removed as it would be if the conductor were not insulated. Thus, to protect the insulation from too much heat, the current through the conductor must be maintained below a certain value. When electrical conductors are installed in locations where the ambient temperature is relatively high, the heat generated by external sources constitutes an appreciable part of the total conductor heating. Allowance must be made for the influence of external heating on the allowable conductor current, and each case has its own specific limitations. The maximum allowable operating temperature of insulated conductors varies with the type of conductor insulation being used. Tables are available that list the safe current ratings for various sizes and types of conductors covered with various types of insulation. The chart in Figure 4-76 shows the current carrying capacity and resistance of copper wire continuous duty wire in bundles at various temperature ratings. Factors affecting selection of conductor material. Although silver is the best conductor, its cost limits its use to special circuits, where a substance with high conductivity is needed. The two most generally used conductors are copper. Wire size. Continuous duty current, amps, wires and bundles. Groups, harnesses, or conduits. See note #1, wire conductor temperature rating. 105 degrees Celsius, 150 degrees Celsius, 200 degrees Celsius. Max. Resistance ohms/1000 ft at 20 degrees Celsius. Tin plated conductor. See note #2. Nominal conductor area. Circ.mils. 24. 22. 20. 18. 16. 14. 12. 10. 8. 6. 4. 2. 1. 0. 0 0. 0 0 0. 0 0 0 0. 2.5. 3. 4. 6. 7. 10. 13. 17. 38. 50. 68. 95. 113. 128. 147. 172. 204. 4. 5. 7. 9. 11. 14. 19. 26. 57. 76. 103. 141. 166. 192. 222. 262. 310. 5. 6. 9. 12. 14. 18. 25. 32. 71. 97. 133. 179. 210. 243. 285. 335. 395. 28.40. 16.20. 9.88. 6.23. 4.81. 3.06. 2.02. 1.26. 0.70. 0.44. 0.28. 0.18. 0.15. 0.12. 0.09. 0.07. 0.06. 475. 755. 1,216. 1,900. 2,426. 3,831. 5,874. 9,354. 16,983. 26,818. 42,615. 66,500. 81,700. 104,500. 133,000. 166,500. 210,900. Note 1. Rating is for 70 degrees Celsius ambient. 33 or more wires in the bundle for sizes 24 through 10, and 9 wires for size 8 and larger, with no more than 20% of harness current carrying capacity being used, at an operating altitude of 60,000 feet. Note 2. For resistance of silver or nickel-plated conductors. See wire specifications. Figure 4-76. Current carrying capacity and resistance of copper wire. 4-47. And aluminum. Each has characteristics that make its use advantageous under certain circumstances. Also, each has certain disadvantages. Copper has a higher conductivity. It is more ductile, can be drawn out, has relatively high tensile strength, and can be easily soldered. It is more expensive and heavier than aluminum. Although aluminum has only about 60% of the conductivity of copper, it is used extensively. Its lightweight makes possible long spans, and its relatively large diameter for a given conductivity reduces corona, the discharge of electricity from the wire when it has a high potential. The discharge is greater when smaller diameter wire is used than when larger diameter wire is used. Some bus bars are made of aluminum which has a greater radiating surface than copper for the same conductance. The characteristics of copper and aluminum are compared in Figure 4-77. Characteristic copper aluminum. Tensile strength pounds/N. Tensile strength for same conductivity. Pounds. Weight for same conductivity. Pounds. Cross section for same conductivity. Centimeters. Specific resistance /millfoot. 55,000. 55,000. 100. 100. 10.6. 25,000. 40,000. 48. 160. 17. Figure 4-77. Characteristics of copper and aluminum. Voltage drop in aircraft wire and cable. The voltage drop in the main power cables from the aircraft generation source or the battery to the bus should not exceed 2% of the regulated voltage. when the generator is carrying rated current or the battery is being discharged at a 5-minute rate. The 5-minute rate in this case means that the battery should last a minimum of 5 minutes in an emergency, with all battery-operated equipment running. Figure 4-78 shows the recommended maximum voltage drop in the load circuits between the bus and the utilization equipment. Nominal system voltage. Allowable voltage drop. Continuous operation. Intermittent operation. 14. 28. 115. 200. 0.5. 1. 4. 7. 1. 2. 8. 14. Figure 4-78. Recommended voltage drop in load circuits. The resistance of the current return path through the aircraft structure is always considered negligible. However, this is based on the assumption that adequate bonding of the structure, or a special electric current return path has been provided, that is capable of carrying the required electric current with a negligible voltage drop. A resistance measurement of 0.005 ohms from ground point of the generator or battery to ground terminal of any electrical device is considered satisfactory. Another satisfactory method of determining circuit resistance is to check the voltage drop across the circuit. If the voltage drop does not exceed the limit established by the aircraft or product manufacturer, the resistance value for the circuit is considered satisfactory. When using the voltage drop method of checking a circuit, the input voltage must be maintained at a constant value. The graph in figure 4-79 applies to copper conductors carrying direct current. To select the correct size of conductor, two major requirements must be met. First, the size must be sufficient to prevent an excessive voltage drop while carrying the required current over the required distance. Second, the size must be sufficient to prevent overheating of the cable while carrying the required current. The graphs in figures 4-79 and 4-80 can simplify these determinations. To use this graph to select the proper size of conductor, the following must be known. 1. The conductor length in feet. 2. The number of amperes of current to be carried. 3. The amount of voltage drop permitted. 4. Whether the current to be carried is intermittent or continuous. 5. The estimated or measured temperature of the conductor. 6. Whether the wire to be installed is in a conduit or in a bundle. 7. Whether it is a single conductor in free air. Suppose that you want to install a 50-foot conductor from the aircraft bus to the equipment in a 28-volt system. For this length, a 1-volt drop is permissible for continuous operation with a conductor temperature of 20 superscript OC or less. By referring to the chart in figure 4-79, the maximum number of feet a conductor may be run carrying a specified current with a 1-volt drop can be determined. In this example, the number 50 is selected. Assuming the current required by the equipment is 20 amperes, the line indicating the value of 20 amperes should be selected from the diagonal lines. Follow this diagonal line downward until it intersects the horizontal line number 50. From this point, drop straight down to the bottom of the graph to find that a conductor between size No. 8 and No. 10 is required to prevent a greater drop than 1 volt. Since the 4-48 continuous circuit voltage 200, 115, 800, 600, 28, 200, 150, 14, 100, 75. Wire length foot 700,630,560,490, 420, 350, 280, 210,175, 140, 112, 98, 84, 63, 56, 49, 42, 35, 7, 400,360,320,280, 240, 200, 160, 120,100, 80, 64, 56, 48, 36, 32, 28, 24, 20, 4, 190, 80, 70, 60, 50, 40, 30, 25, 20, 16, 14, 12, 50, 45, 40, 35, 30, 25, 20, 15, 12, 10. Amperes. 1, 1.5, 2, 3, 4, 5, 7, 10, 15, 20, 30, 50, 70, 100, 150, 200, 300, 87, 6, 4, 3, 2, 98, 7, 6, 5, 1, 0.5, 24, 22, 20, 18, 16, 14, 12, 10, 8, 6, 4, 2, 1, 1/0, 2/0, 3/0, 4/0. Voltage drop. Closing brace. Example 1, Example 2. No. 8 wire at 20 amps No. 12 wire at 20 amps No. 14 wire at 20 amps. Wire size. Voltage drop chart continuous flow at 20 degrees Celsius tin plated mil W 27759. Conductor. Note: length L is based on conductor temperatures of 20 degrees Celsius to determine length L2. At a higher conductor temperature, use formula where T2 equals estimated conductor temperature degrees Celsius. L2 equals 254.5, L1, 234.5, plus T2, figure 4-79. Conductor graph. Continuous flow. Indicated value is between two numbers. The larger size, no, 8, should be selected. This is the smallest size that should be used to avoid an excessive voltage drop. If the installation is for equipment having only an intermittent maximum 2 minutes requirement for power, the graph in figure 4-80 is used in the same manner. Conductor insulation. Two fundamental properties of insulation materials, for example, rubber, glass, asbestos, and plastic, are insulation resistance and electric strength. These are entirely different and distinct properties. Insulation resistance is the resistance to current leakage through and over the surface of insulation materials. Insulation resistance can be measured with a meter without damaging the insulation. This serves as a useful guide in determining the general condition of insulation. However, the data obtained in this manner may not give a true picture of the condition of the insulation. Clean, dry insulation having cracks or other faults may show a high value of insulation resistance, but would not be suitable for use. Dielectric strength is the ability of the insulator to withstand potential difference, and is usually expressed in terms of the voltage at which the insulation fails due to electrostatic stress. Maximum dielectric strength values can be measured by raising the voltage of a test sample until the insulation breaks down. Because of the expense of insulation, its stiffening effect, and the great variety of physical and electrical conditions under which the conductors are operated, only the necessary minimum insulation is applied for any particular type of cable designed to do a specific job. The type of conductor insulation material varies with the type of installation. Rubber, silk, and paper insulation are no longer used extensively in aircraft systems. More common today are such materials as vinyl, cotton, nylon, Teflon, and rockbestos. 4-49. Circuit voltage. 200. 115. 1600. 1200. 28. 400. 300. 14. 200. 150. 1400. 1260. 11. 2980,840. 700. 560. 420,350. 280. 224. 196. 168. 126. 112. 98. 84. 70. 14. 800,720,640,560. 480. 400. 320. 240,200. 160. 128. 112. 96. 72. 64. 56. 48. 40. 8. 200,180,160,140. 120. 100. 80. 60. 50. 40. 32. 28. 24. 18. 16. 14. 12. 10. 2. 190. 80. 70. 60. 50. 40. 30. 24. 20. 16. 14. 12. 8. 6. 4. 1. Amperes. 1. 1.5. 2. 3. 4. 5. 7. 10. 15. 20. 30. 50. 70. 100. 150. 200. 300. Wire length foot. 24. 22. 20. 18. 16. 14. 12. 10. 8. 6. 4. 2. 1. 1/0, 2/0, 3/0, 4/0. Voltage drop. Wire size. Voltage drop chart. Intermittent flow at 20 degrees. Tin plated mil W27759. Conductor. Note: length L is based on conductor temperatures of 20 degrees Celsius to determine length L2. At a higher conductor temperature, use formula where T2 equals estimated conductor temperature degrees Celsius. L2 equals 254.5, L1, 234.5, plus T2, figure 4-80. Conductor graph. Intermittent flow. Identifying wire and cable. To aid in testing and repair operations, many maintenance activities mark wire or cable with a combination of letters and numbers that identify the wire, the circuit it belongs to, the gauge number, and other information necessary to relate the wire or cable to a wiring diagram. Such markings are the identification code. There is no standard procedure for marking and identifying wiring. Each manufacturer normally develops its own identification code. Figure 4-81 illustrates one identification system and shows the usual spacing in marking a wire. Some system components, especially plugs and jacks, are identified by a letter or group of letters and numbers added. H215 820 H215 820 H215 820. Figure 4-81. Spacing of printed identification marks. To the basic identification number. These letters and numbers may indicate the location of the component in the system. Interconnected cables are also marked in some systems to indicate location, proper termination, and use. In any system, the marking should be legible, and the stamping color should contrast with the color of the wire insulation. For example, use black stamping with light-colored backgrounds, or white stamping on dark-colored backgrounds. Most manufacturers mark the wires at intervals of not more than 15 inches lengthwise, and within 3 inches of each junction or terminating point. Figure 4-82. Coaxial cable and wires at terminal blocks and junction boxes are often identified by marking or stamping a wiring sleeve rather than the wire itself. For general-purpose wiring, flexible vinyl sleeving, either clear or white opaque, is commonly used. For high-temperature applications, silicone rubber or silicone fiberglass sleeving is recommended. Where resistance to synthetic hydraulic fluids or other solvents is necessary, either clear or white opaque nylon sleeving can be used. 4-50.